Good afternoon. This is Mrs. Boland with the University of West Florida. I'm putting together a quick answer key for as much time as I have to put this together for my stats class. I've asked my children to reduce the background noise, but not to worry about being completely quiet, so you'll probably hear some random talking in the background. Hopefully that will still work for you guys. Hopefully we'll hear dishes being washed and some floors being swept, and yes, this is my subtle hint at what they're supposed to be doing. Haha. Okay, let's get busy. So we have a simple random sample of 40 salaries of NCAA football coaches. Has a mean salary of, wow, I think I am definitely in the wrong business. So let's see here. Let me get a highlighter here. So we have 40 salaries of the NCAA football coaches, and the mean salary is $415,953. Assume that the population, that's key right there. Standard deviation is this figure. Construct a 95% confidence interval for the coach's salary. So what we want to look at is the fact that we know the population standard deviation. Population standard deviation. Okay, and we're doing a 95% confidence interval. So we have our sample size is 40. We have our mean is 415,953. We have population standard deviation, which is sigma. We're doing a 95% confidence interval. Okay, because we were given, and actually this symbol right here, assume that the population is out of 40, so that should be an X bar. So let me change that real quick to X bar. There we go. So our formula is like this. It says X bar plus or minus Z sub C multiplied by sigma divided by the square root of n. So I need to look up what is my Z sub C. I know my X bar value. Whoops. X bar value is this value right here. I know my sigma. It's right here. I know my sample size. It's right here. And okay, so here is my Z table. And on your Z table at the very bottom, we have the confidence, the critical values. So we wanted a 90%, let me go back and double check that, 95% confidence level. So we're going to come in here and we're going to say at 0.95, our Z value is 1.96. So our critical value, Z sub C, is 1.96 when C is equal to 0.95 or 95%. So my critical value is 1.96. So we're going to come back in here and we're going to say that Z 0.95 is equal to 1.96. So here we go. We're just going to fill in everything we know. And so we have 415,953 plus or minus 1.96 multiplied by 463,364 divided by the square root of 40. Okay, and we're going to grab our calculator and we will find out, where's my calculator? There's my calculator. Hit clear. So I'm going to go 415,953 minus 1.96 multiplied by 463,364 divided by my second, and is it my log? Let me look at my own calculator. Nope, it's the x squared. Right there, that brings up my square root, and my sample size is 40, and I hit enter. And I end up with 272,355. So 272,355. So 272,355 point, and I will go pick up those decimal places. 00. We're going to take that as It's 0, 1. We'll round properly. Okay, and now we're going to highlight the equation, hit enter, and that re-brings up that equation. And we're going to hit this arrow button until we get over to the negative sign, the subtraction sign right there, and we're going to hit plus. And now we're going to hit enter again, and that brings up with it being added on. So that is 559,550, and we're going to go ahead and put 99 on there, but 559,550. 559,550.99. So in reality, we essentially have that we are 95% confident that the true, oops, there we go, that the true average salary for NCAA coaches is between $272,355 and $559,551 is what I would say. I would round that up 1 penny and down 1 penny. Okay, so I paused the video for just a second to type up the interpretation. So pause the video if you need to copy it down. Okay, and here's our next one. And I should also say I've never solved these problems before, so if you see me make an error, please bring it to my attention. Those things do happen sometimes when my family is around and my mind's not 100% focused on my task at hand. Okay, so a simple, let me grab my highlighter real quick. So a simple random sample of 50 adults, so that tells me my sample size is 50, including males and females, is obtained, and each person's red blood cell count in cells per microliter is measured. The sample mean is 4.63. The population standard deviation for the red blood cells is 0.54. Construct a 99% confidence interval estimate with, of the mean red blood cell count of adults. So let's write down what we know. We know that our sample size is 50. That's right there. We know that our sample mean, X bar, is equal to 4.63. We know that our population standard deviation, denoted as sigma, is 0.54. And we know that we are looking for a 99% confidence interval. Okay? And because we know sigma, we are on a Z table, Z distribution, and we're looking for a 99% confidence, so we're going to look at Z.99. So let's switch tables real quick. So 0.99 is right here. My Z value then is 2.58. So this is equal to 2.58. So if I'm going to be calculating a confidence interval, I'm going to end up with X bar plus or minus Z sub C times sigma divided by the square root of n. So we're just going to plug that in, and that is equal to 4.63 plus or minus 2.58 multiplied by our standard deviation 0.54 divided by the square root of 50. And we're going to put this in our calculator, and we're going to find out that it is equal to, clear, well, I guess I need to turn it on first, clear, and so we're going to have 4.63 minus 2.58 multiplied by 0.54 divided by the square root. What's my sample size? 50. 50. And I hit enter, and I get 4. And I get my lower bound to be 4.43. It would be to 9, the 9 would round up to 0, so we will put 30, comma, and we're going to grab our other, we're going to go back up. Let's see here, we hit this, nope, wrong thing. How about this? And hit that, and that brought up our, well, okay, so that didn't. Let me hit clear and just type it in again. Okay, so I typed it in again, and there is the correct interval, and it's going to be 4.8270. So there is our confidence interval. I would like to show you a different technique to solving confidence intervals. So, let me turn this so I can see my computer screen a little bit better. You're going to hit Stat. You're going to come over to Test, and then you're going to scroll down to Z interval. It says Z interval. That means you're doing a confidence interval using the Z tables. We're going to hit Enter. And on this one here, we don't have raw data. We have statistics. So we're going to come over and we're going to highlight statistics. And then we're going to scroll down, and it says, what is my population standard deviation? My population standard deviation is the 0.54. So I'm going to change this 0 right here to 0.54. And I'm going to come down. Oops, hold it. Somehow I got back on data. Let me go back up there and get over to stats. Hit Enter. There we go. So we come down. We have 0.54 for our standard deviation for population. Now we're going to come down, and we're changing our mean to be 4.63. So that's 4.63. Then we're going to come down. My sample size is 50. So I'm going to input my sample size of 50. And then I'm going to come in here and I'm going to put the confidence level that I'm interested in, which is 0.99. So I'm going to put 0.99. I'm going to hit Enter, and I'm going to tell it to calculate. And if you look, we come up with essentially the same thing, 4.4333. I'm missing an extra 3 there. That's just a rounding error. And then 4.8267. So again, that's just a little bit of a rounding error because the calculator is using a precise Z value, more precise than what you and I are using off of tables. So if you put this answer down right here on your exam, or this answer, you'll get full credit either way. But I want you to write down your calculation, your equation right here. Okay, that's very important, even if you're using the calculator to help you out. Okay, now it says the normal range of red blood cells for adults is given by the National Institute of Health as 4.7 to 6.1 for males and 4.3 to 5.4 for females. What does the confidence interval suggest about these normal ranges? If you look right here, you're going to see that our lower bound is 4.4 and our upper bound is 4.8. And you can see that men's average red blood cells is higher on average when you look at just gender. Gender specific, men have a higher red blood cell count than women. So that when we average them together, okay, it really shifts the mean down. Matter of fact, it shifts the mean down a good bit. So what does the confidence interval suggest about the normal ranges? This confidence interval here says that these ranges are higher than what we would expect because our confidence interval here says that the average for the combined gender is lower than what the normal standard is. And in fact, I would say that even for the females could not have had that much of an influence unless the sample here was not proportionate. If it had a lot of females in it, let's say, because it says including males and females, sometimes a really strange sample could have been randomly taken and maybe you had 48 females, 2 males, but even this seems awfully low. So what this suggests to me is that the National Institutes of Health may want to reevaluate their what they consider to be standard normals for the different genders. Okay, the ages of 19 actresses at the time that they won Oscars for Best Actress categories have a mean of 35.8, so that's ages, and a standard deviation of 11.3 years. How did we get the standard deviation? We got the standard deviation by calculating it off of the 19 actresses. This tells you this is not a population standard deviation. This is a sample standard deviation. Assume that the sample is a simple random sample. Construct a 99% confidence interval estimate of the mean age of actresses at the time that they won the Oscars for the best Oscar or best actress category. Because of the information that we've been given, we will not be using Z, but we will be using T. So let's write down what we know. We have, let me switch to highlighter. We have 19 actresses, and we're looking at the mean age, and the sample mean gave us 35.8 years of age and a sample standard deviation. It does not say the word sample, but because it doesn't say population, we are going to assume that this standard deviation came from the 19 actresses. Assume that the sample is a simple random sample. Construct a 99% confidence interval of the mean age of actresses at the time that they won their best actress category. So we need to write down that our sample size is 19, that our X bar is 35.8, that our sample standard deviation, notice I use S, is 11.3. Therefore, because we have a sample standard deviation because of that one factor, we will use a T distribution. This tells us that our population standard deviation is not known. Therefore, we are going to approximate it using our sample standard deviation, which is denoted by S. Okay. So we are told to get a 99% confidence interval. 99% CI. I need to know what my degrees of freedom are. If I'm on a T, and I'm going to say my degrees of freedom, remember, are equal to n minus 1, which is 19 minus 1, which is 18. I need to get my T point 99, comma, 18 degrees of freedom, so I know what that critical value is. So we're going to open up real quick my T. And what did we have as our degrees of freedom? 18 and 99. So 18 degrees of freedom. And we're looking at 99% confidence. We're going to look at the intersection of the two. So 0.99 and 18 is 2.878. So 2.878. So 2.878. Our formula is X bar plus or minus T 0.9918 multiplied by S divided by the square root of N. So we will plug all of this in and we will have 35.8. I don't have a disappearing ink. Multiplied by 2.878 multiplied by 11.3 divided by the square root of 19. We're going to put that in our calculator. Okay, so we're going to bring up our calculator and we're going to punch this in and hit clear. And we're going to have 35.8 minus 2.878 multiplied by 11.3 divided by, let me undo that, divided by the square root of 19. And we hit enter, and we get 28.3391. So my lower bound is going to be 28.3391, and my upper bound, again using my calculator to my fullest advantage, we're going to hit that, then enter, and then we're going to come over here. We're We're going to change that to plus sign and hit enter. And the answer is going to be 43,000 or 43 point, not comma, 2609. Okay, so I'm 99% confident that the true population mean average of women who won Oscars for the Best Actress category is between 28.33 and 43.26. Let's go ahead and repeat this test real quick, demonstrating the ability of the TI-84. And again, we're going to hit Stat. We're going to come over to Test. We're going to come down to not a Z, but a T, because remember, we're right here where you're doing a T-test. So we're going to do a T interval, and we're going to hit Enter. And we have summary statistics, so we're going to hit Enter again. Okay, maybe we're just going to hit the down arrow. Our X bar is 35.3 or 35.8. Our sample standard deviation is 11.3. Our sample size is 19. Our confidence level is 99. So we're going to hit calculate. And here is our confidence interval. So it's 28.338. So a little bit difference again because the TI-84 has the ability to round off and be more precise to 43.262. So again, a small rounding error, but not much. And both answers would be 100% correct on the exam. Let's look at our next problem here. It says a test of the effectiveness of garlic for lowering cholesterol. 27 subjects were treated with Garlicin, which is garlic in a processed tablet form. Cholesterol levels were measured before and after the treatment. The changes in their LDL cholesterols have a mean of 3.2 and a standard deviation of 18.6. Construct a 95% confidence interval for the mean net change in the LDL cholesterol after the treatment. Okay, so when we look at this particular problem, you're going to notice that it does not give us a population standard deviation. It gives us just a standard deviation of the study, the 27 subjects. So let me grab my stylus, which I put over here. And let's highlight our important information. So in a test of effectiveness of garlic, 27 subjects were treated. We have a mean of 3.2 and a standard deviation of 18.6. Construct a 95% confidence interval. So we have our sample size is 27. We have X bar is 3.2. We have S, which is 18.6. We are looking for a 95% confidence interval. We know that our degrees of freedom is going to be 27 minus 1, which is 26. And we know that we need a T of 0.95, comma 26. And let's look up our critical T value. So 95% confident and 26 degrees of freedom. So 26 degrees of freedom right here at the bottom. Let me scroll up a little bit. And 95 is right here. So let's scroll right there. And we're looking at 26. So right here is our 26. So 2.056. 2.056. X bar plus or minus T of 0.95, 26 times S divided by the square root of N. Okay, that's our formula. Make sure you're looking at your formula sheets so you know how to use your formula sheets tomorrow. So this is going to be 3.2 plus or minus 2.56. Oops, let me erase that. 2.056 times 18.6 divided by the square root of 27. So this is going to be equal to, and grab our calculator, punch it in. Okay, so we have 3.2 subtract 2.056 multiplied by 18.6 divided by the square root of 27. Hit enter, and you're going to see that that is negative 4.1595. So that is negative 4.1596, comma, and now we will just simply bring up our calculator again, go up and highlight that, hit enter, and then we're going to scroll right on over and change our negative sign, our subtraction sign, to a plus. Go from subtraction to addition right there, hit enter, and our new value is 10.55959. So we'll be running that up. So that is 10.5596. Okay, so this is our confidence interval right here. Let's go ahead and double check and show how we do that in the TI-84. So you hit stat, you're going to come over to the test, you're going to scroll down till you get to T interval, and you're going to hit enter. We're going to do statistics, and we're going to have a mean of 3.2. We're going to scroll down. Our standard deviation is 18.6. Scroll down. Our sample size is 27, and we're doing a 95% confidence, so we've got to change that to 95 and hit enter. And there is our confidence interval, exactly what we just calculated over here. Little minor rounding errors. Okay, our next problem. Oh, hold it. It says, what does the confidence interval suggest about the effectiveness of garlic? Okay, because this contains the 0.0. Okay, think of a real number line. You have -4. Then you would have 0, and then you have 10 on the other side, right? Because this interval contains 0, we cannot really conclude that there is a actual change or lowering of the cholesterol, okay? And it's because this interval contains 0. Okay, a Pew Research Center poll of 1,501 randomly selected U.S. adults showed that 70% of the respondents believe in global warming. Find a 95% confidence interval for the population proportion of adults that believe in global warming. If any one of these people who believe in global warming had done significant study in the cyclical nature of our weather, they might rethink their conclusions. An excellent book to read and study on that is called The Endurance. It's by Shackelford, and it is an excellent book. And you can read about his diary. It's his diary and his journal of going to, I don't remember if it's the Arctic or Antarctic. It's one of the two. And talking about the melt-offs and things of that nature, and the cyclical features of the weather that he compared to prior and after explorers, and how things went back to freezing versus melting off, etc. So anyway, just something else there to consider. So back to statistics. This is a proportion. So we have randomly selected 1,501 randomly selected adults. We have 70% believe in global warming. We want a 95% confidence interval. So that's going to look like this. So N is equal to 1501. P is, or P hat, is going to equal to 0.7. Q hat is going to equal to 0.3 because remember Q is 1 minus P. So that's 1 minus 0.7, which is 0.3. We are looking for a 95% confidence interval. So we're going to have P hat plus or minus. And remember, when it comes to proportion, we are always on the Z table. So our Z of 0.95, again, we'll come over here, we'll pull this up, 0.95, my Z value is 1.96. So that is equal to 1.96. So it's going to be P hat Z sub C multiplied by, and I'm just going to go ahead and pull up our formula sheet real quick. And here's our formula sheet. Let's get to page 3, which is where we need to be. And here's our confidence interval about the mean. So here's our error. So it's going to be the square root of P times Q divided by N. So P times Q divided by N. So P hat times Q hat divided by N. And we'll just plug in everything that we know. So P is 0.7 plus or minus 1.96. 1.96 multiplied by 0.7 times 0.3 divided by 1,501. And we'll punch that in our calculator and we will get lower and upper boundaries. Remember, when we're doing proportion, we want to go with 6 decimal places, not our standard 4. So that's going to be 0.7 subtract 1.96 times the square root. And I'm going to go ahead and put this in parentheses. Don't have to, but it makes me feel more confident in the order of operations. And I'm going to close that. I'm going to hit enter. And so my lower boundary is 0.676816, but that 6 is going to round up to a 7. Okay, so to change this one again, you just simply go up, grab it, hit enter, scroll over to the left several times, hit a plus sign, hit enter, and you have the new value. And I may have only gone to 5 decimal places there. Sorry about that. Should have been 723, a 3 right after that, another 3. Okay, so that is this one here. Again, we'd be 95% confidence that the true proportion of people in the United States, adults in the United States, that believe in global warming is between 67.68% and 72.31%. Okay, here is another one. Let me double check and make sure I have voice. You know, I never checked. Yes, I do have audio. Good. Okay, so a survey of 1,002 people, 701 said that they voted in a recent presidential election. Voting records show that 61% of eligible voters actually did vote. Find a 99% confidence interval for the estimated proportion of people who say that they voted. So right here, we actually know the true percentage. Okay, so we don't even have to come up with a confidence interval because we know that 61% of eligible voters actually did vote. But what we want to know is, the question is develop a 99% confidence interval estimate for the proportion of people who say that they voted. Okay, so we'll be able to compare what people say to what to see if how that actually compares to what we know to be fact, and the fact is the 61%. So we have our sample size is 1,002 people. X, how many people said yes? 701. So therefore, P hat is going to be equal to 701 divided by 1,002. Q hat is going to be equal to, let's put this in a decimal form real quick. So 701 divided by 1,002 is equal to 0.6996. So we go 1 minus 0.6996. 0.6996. And that's going to be 0.3004. Okay, so I have p hat plus or minus. Oops, let's see, we're going to be on a z, and our z at 0.99 is going to be 2.58, I think. Let's double check that though. 99, 2.58. So there we go. So this critical value is 2.58. So it's p plus or minus 2.58, or the critical value, times the square root of p times q. So this is going to be 0.6996 times 0.3004 divided by 1002. Okay, and of course our p there is right here is the 0.6996. So let's go ahead and grab our calculator and bring this up, put it on. So I have 0.6996 subtract 2.58 multiplied by the square root of 0.6996 multiplied by 0.3004 divided by 1002. And there we go. Okay, so here's our interval. I'll let you verify the calculations. I'm trying to get this video to be shorter than what it is right now, so I'm going to start moving a little quicker, recognizing the fact that you can hit pause, replay, rewind, whatever. Okay, are the survey results consistent with the actual voter turnout of 61%? Actually, no, they're not, because we know from the data that we can factually collect, we know exactly what percentage of registered voters did vote, and that is 61%. And when we talk to people in our survey, in this case of 1,000 people, the voting response was higher. It's from 66 to 74% almost. Okay, so typically people probably are. I would guess that one of the reasons we may have, out of a $1,000 question, received a falsified increase is because of people's embarrassment of saying no, they did not take and exercise their legal right as a voter and vote and participate in the election. And people are often embarrassed by the fact that they do not do what they have the legal right and opportunity in the United States of America to do. So that's probably why the bias is higher. Okay, a researcher collected a simple random sample of cents proportions from 100 checks and from 100 credit card charges. The cents proportion of the checks have a mean of 23.8 cents and a standard deviation of 32 cents. The cents proportion of credit card charges had a mean of 47.6 cents and a standard deviation of 33.5 cents. Construct a 95% confidence interval for the mean difference between the cent proportion of credit cards and checks. What that's saying is when you write a check to Publix or Walmart or wherever, your total may be $59.48. So what they did is they looked at the 48 cents, okay, and they did a random sample of 100 checks and then 100 credit cards. And I'm actually surprised with the credit cards that we had such a, you notice the standard deviation for the checks is smaller than the standard deviation for the credit cards. And that surprises me because so many people, when they tip and stuff, round off to an even number. So I would have expected there to be a lower variance, a smaller variation in the credit card. So that's interesting. So it says construct a 95% confidence interval for the mean difference of the proportions. So, or mean credit card of cents. So let's highlight what's important and get busy working here. So let's go this right here. So researchers collected a simple random sample of 100 checks, 100 credit card charges. We're reading through. So from the checks, we have a mean of 23, standard deviation 32. So that's going to be a sample standard deviation. The cents portion of credit card charges has a mean, so credit card, of 47 and a standard deviation of 33.5. Again, that is a sample standard deviation. Construct a 95% confidence interval. So here we go. So we're going to have two populations. I'm going to let population 1 be my checks. I'm going to let population 2 be my credit cards. Okay, so my sample size for population 1, n sub 1, is equal to 100. My sample size for my population 2 is also 100. My X bar for population 1 is right here for checks, and that is 23.8. And then it gives me my standard deviation next. So S sub 1 is equal to 32 cents even. 32 cents. Whoops, 32 cents even. Now, going over to population 2, my mean is 47.6. Oops. Let's see if my computer is getting hot. It has a harder time keeping things the hotter it gets. Okay, and then my standard deviation is going to simply be S sub 2, and that is equal to 33.5 cents. Okay, and we're constructing a 95% confidence interval. And because we do not have population standard deviation, we are on a t distribution. Oh boy, this is going to be hard, isn't it? Distribution. Sorry, I had to pause the video in order to work on getting the word distribution written down. Okay, so we are going to need a critical value for our t, and our t critical value is going to be at, what is it, 95%. So it's 0.95. And how many degrees of freedom? We go off the smaller of the two, but in this case they're equal, so it doesn't matter. So it's going to be 99. So 99 degrees of freedom. So df is equal to 99 and minus 1. And let's see here, coming over here, so we're at a 95% and 99. So I don't have 100 here. I don't have 99. So we're going to go down to 80. And we are going to a 95%. So 95% is, oops, hold on, I picked up the wrong table there, didn't I? T table, there we go. So 95% is this column right here. And we're going to go down to right at 80. Because we're going to go smaller on our degrees of freedom. So it's 1.99. So we're going to use 1.99. Okay, let's go find our formula, because this formula is not as pleasant as some of the others. Well, it's okay. It's right here. Here is our formula right here. Okay, so it's going to be the difference. We're going to subtract mu1 minus mu2, but we don't have mu1, so we're going to do x bar 1, x bar 2 subtraction, and then we're going to calculate the error. So here we go. So we have x bar 1 minus x bar 2 plus or minus our critical value. So that's z sub c. Or nope. Sorry. That's t. So c comma df. Okay, multiplied by s1 squared divided by n1 plus s2 squared divided by n2. And let me double check my formula just real quick to make sure I copied that down right. I'm sure I did, but yeah, there we go. And we're simply going to fill in all the numbers. And so we have x bar 1 is 23.8 subtract 47.6 plus or minus my critical t value, which is 1.99 times my standard deviation is 32 squared divided by my sample size of 100 plus 33.5 squared divided by 100, just like that. We're going to put this in our calculator. And we're going to write our answers right here. So let's pull up our calculator, turn it on, and we're going to clear it out. We're going to open up parentheses, and we're going to go 23.8 subtract 47.6, close parentheses. Okay, now that makes that subtraction happen. So now we're going to go subtract. We're going to go 1.99 multiplied by our shift to get our standard or our square root. Open parentheses and go 32 squared divided by 100. Close parentheses plus open parentheses, and that's going to be 47.6. 47.6. I'm going to square this 47.6 a different way, and I want you to see what happens on the calculator and how you have to make sure you deal with it properly. If I decide to use the caret button and hit 2, you notice I'm still up at the caret position right there. So I actually have to take and use this button right here to move it back down. If I didn't do that, I would actually be dividing the 2 when I hit divide, okay, because it wouldn't come down. So divide by 100, close my parentheses, hit equal. And there is my lower boundary. Okay, so here's our confidence interval right here. And the proper interpretation would be that I'm 95% confident that the true difference between the means of check cents and credit card cents, the true mean difference is between negative 35.21 and negative 12.38 cents. So by the fact that I have a negative number tells me that there's more variation and larger cents in the credit cards. It means I did checks subtract credit cards. I ended up with a negative number, which tells me that there's more cents in the credit card because I had a negative number than there are in the checks. Okay, I had to skip a couple problems because I'm only working on this for 1 hour and I'm up after this problem. So I wanted to go ahead and do this particular problem real quick because it has to do with the proportion. So it says among 2,739 female atom bomb survivors, 1,397 developed thyroid disease. Among 1,352 male atom bomb survivors, 436 developed thyroid disease. Sorry about that. Okay, construct a 95% confidence interval for the difference of proportions of thyroid disease in female survivors and the proportion of thyroid disease and male survivors. So here we go. So we have two different populations. I'm going to let population 1 be female atom bomb survivors. And we're going to let population 2 be male atom bomb survivors. And so we have the sample size in 1 is equal to 2,739. X1 is going to equal 1,397. We have N2 is equal to 1,352. And we have X2 is equal to 436. We are constructing a 99% CI. Because it's going to be proportion, we are on a Z, so we're looking at Z99, and that's going to be 2.58. Okay. Let's see here. And we're looking at the difference between the survivors, or the difference between male and female. So let's get p hat 1. And p hat 1 is going to be 397 divided by 2,739. P hat 2 is going to be 436 divided by 1,352. And then Q, let's just see what this calculates. 397 divided by 2739. And that's going to be equal to 0.144943 and 436 divided by 1352, and that is equal to 0.32248. 5, 1, 2, 3, 4, 5, 6. There we go. Alrighty, and then Q1 is equal to, let's see here, 1 minus 0.144943 is equal to 0.855057, and Q hat 2 is going to be equal to 1 minus 0.322485, and that is equal to 0.677515. Let's go find our formula. We're going to come over here to our formula sheet, which is right here, and this is the formula that we're going to be using. So we're going to take p hat 1, subtract p hat 2, then we're going to add and subtract to it this right here. So it's the square root of p times q, p1 q1 divided by n1 plus p2 q2 divided by n2. So write down our formula real quick, and we're going to end up with p hat 1 minus p hat 2 plus or minus z sub c times the square root of p hat 1 q hat 1 divided by n1 plus p hat 2 q hat 2 divided by n sub 2, all underneath the radical. And I'm just going to flip back to double check to make sure I copied it down right, and I did. And now we're just going to substitute in our values. So we know that p hat 1, and to make it easier, I'm just going to go 397. Actually, no, I won't. I'll go ahead and use decimal form. So 0.144943 subtract 0.322485 plus or minus 2.58 on the square root of 0.144943 times 0.855057 divided by 2739 plus 0.3224 322, come on, my computer, come on, computer, 2485 times 0.66, no, 677515. Whoa, crazy. Let's see if we can get that straightened out. There we go. Divide it by 1,352. And that's your formula. So we're going to plug that into our calculator, and I'm not going to demonstrate that, how to plug that in on the calculator. I want you to duplicate my answers. Okay, so here is our final answer right here. Right, there's our final answer. I want you to take your time and double check. Let me know if I made a mistake. But I want you to make sure that you know how to put this in your own calculator and that you can duplicate the math calculator usage and order of operation. Okay, so what does this mean? This means that the difference between the portion of women survivors versus men survivors thyroid disease that actually men have more thyroids. The proportion of men have developed thyroid more than women. Okay, and the reason I say that is because it's negative. So we're subtracting a larger number, which means a larger proportion of men. We're subtracting a larger number from a smaller number, and we subtracted the men from the women. Therefore, the men have a larger proportion of thyroid disease, and the interval does not contain 0. So that shows the shift that we can conclude then that men who survived the atom bomb have a higher rate of thyroid disease compared to women who survived the atom bomb. And that should do it. That puts us right at 60 minutes. I hope this video is helpful.